So far, what we've considered are waves that move along, and as they do, they transfer energy. And because they're transferring energy, we can say that these waves are progressive as they progress along. But what I'd like to look at now are another type of wave, and this kind of wave, it doesn't transfer energy, but it stores it. And what we're going to look at instead are waves that don't seem to move at all, and these are called standing or stationary waves. So it's these standing or stationary waves where we store energy, and they're quite different to the progressive waves that you've been used to so far. So how are these waves formed? Well, if we have a progressive wave that is moving along and it reflects off some kind of boundary or perhaps an endpoint, the reflected wave will come back, and this time the reflected wave will have the same kind of amplitude and phase difference, and it's the interaction of these two waves where we look at superposition and the overall resultant that gives us a standing wave. What I'm going to look at here is a series of standing waves that we can have set up perhaps on a string, and provided we have a fixed end at both sides, the wave that we set up can't move up and down at the ends because it's in a fixed position. And what I have here is the first standing wave that we produce, and what we have is at the end it can't move, and this is what we call a node, or effectively there's no displacement at the node. We also have a point of maximum displacement, which is an opposite to a node, and this is what we call an antinode. And all I've drawn in here is effectively the maximum and the minimum position of perhaps a string which is vibrating. I can repeat it for perhaps a second kind of standing wave that we can fit in. So again, we're going to have the ends must be constrained. But this time there's another wave that is actually the length of one complete wavelength. And if I draw that as one of its waveforms, the opposite to this at the other extreme, half a cycle later, looks a bit like this. And again we have a node at each end. We also have a node, or a point of no displacement in the middle, and then we have an antinode and another antinode. Now the key thing about this is that because this is one wavelength, the distance from a node to another antinode is equal to the wavelength of that wave over 2. In this one here, this is also equal to the wavelength over 2, and so on. And if we repeat the process, what we have here, although they're slightly dodgily drawn, we do have various other standing waves that can be set up within the same distance. From the diagram so far, they all look a bit static, so this is what it would look like. Here we have a couple of nodes and the particles moving up and down in the middle, and then we also have another wave that has 3 nodes and also one that has 4. Looking in a bit more detail at these various diagrams here, perhaps we have a string that has length L. And what we have here is the first standing wave that we can produce. What we call this is the fundamental. For this fundamental, because the length is equal to the wavelength over 2, we can say that the wavelength is equal to 2L. And this happens at a certain frequency, which we call F0 or F0. And that is the fundamental frequency of that standing wave. Now there's another one here. This time, what we call this is the second harmonic. The reason being that the fundamental frequency is the first harmonic, and the second harmonic, the wavelength is equal to the length of that string, and we call this, where it basically has twice the frequency of the first one. And what we then have is the third and the fourth. And what we find with many musical instruments is that because we have all these harmonics, we have various multiples of that fundamental frequency. So what we find is that there are a number of modes of vibration, various harmonics, and we still have the nodes and antinodes, and as we have a higher and higher frequency, we can see the wavelength gets smaller and smaller.